All right, starting lecture B right now. We'll start by talking about properties of limits and continuous functions. Here are some limit properties. I'm describing these things in words. They can be described with equations. I think what I'll do is I'll do an example where we use one of these or a couple of these properties, and we'll see how these properties play out with equations. First property is that the limit of a linear combination of functions is the corresponding linear combination of their limits. That's a mouthful. That's probably worth writing down what it means right away in an equation. The limit as x approaches c, where c could be a number. That's most typically what people think about here. Or it actually could be plus or minus infinity. Could be a number or plus or minus infinity. What's a linear combination? We'll keep it to the simplest case. A combination of two functions. Some constant a times a function f of x plus some other constant b times another function g of x. That expression is called a linear combination of f and g. If a and b were 1, then it would be the sum of f and g. If a was 1 and b was negative 1, then it's really the difference, f minus g. So that's the limit of a linear combination. What does this property say? It says it's the corresponding linear combination of their limits. What does that mean? It means the answer is this. A times the limit as x approaches c of f of x plus b times the limit as x approaches c of g of x. That's the corresponding linear combination of their limits. Their limits, if they exist, are numbers. This is just a times some number plus b times some other number. This is the corresponding linear combination of their limits. I hope it makes intuitive sense. If f of x is approaching, for example, 5, and g of x is approaching 7 as x approaches c, it should make sense that this function, where, say, a and b are both 1, would approach 5 plus 7. If the outputs of f are getting closer and closer to 5, and the outputs of g are getting closer and closer to 7, and a and b are both 1, then f plus g should get closer and closer to 12. Question?
Yeah, I know that a and b are like coefficients, but what exactly is the application? Like, why would there be coefficients?
I don't want to take the time for that right at the moment, because I can't think of an example right off the top of my head. But I'll think about it after class and get back to you. Thanks for asking. Second property, the limit of a product of functions is the product of their limits. Again, all this is assuming the appropriate limits exist. So if I'm taking the limit of f of x times g of x as x approaches c, I get the corresponding product of their limits, assuming those limits exist. I'm putting parentheses around these limits to emphasize they are individual numbers, though often you won't see people put parentheses like that. And again, I hope that makes sense. If f is approaching, so we don't have any a and b anymore. If f is approaching 5, its outputs get closer and closer to 5, and g is approaching 7, it should make sense their product approaches 5 times 7, or 35. Because you're multiplying the outputs. And you can do the same kind of thing with the quotient. The limit of a quotient of functions is the quotient of their limits, quotient with fraction. Divide. Assuming we're not dividing by 0. So instead of a dot in here, I could put a slash for divide, like that. Pretend it's a fraction. Pretend both of these are fractions. This is the limit of a fraction, a quotient. This is the quotient of their limits. As long as we're not dividing by 0. As long as the limit of g is not 0. Can't divide by 0. Here's an example where these rules can be used. I'll write it over here. We're going to have some completion problems on Wednesday, similar to this. I'm going to go ahead and use these properties, but I am going to technically do it in kind of a sloppy way, you might say, and that's okay for you as well. Let's take the limit of that rational function as x goes to infinity. You should be able to look at this and just say the answer based on what I told you last week. What's the answer?
1/3.
1/3, right? The degree of the top and bottom are the same, 1. So you look at the coefficients of the ratio of the coefficients of the highest powers of x. 1 and 3. The answer is going to be 1/3. Now I've told you before this point that you can just say that's the answer. But you should be able to also confirm it with the following calculation. I'm going to use these properties, but I need to do a little trick first. And the trick I need to do is I need to multiply the top and the bottom by 1 over x. 1 over the highest power of x. That's the trick that must be done. I'll explain why here in a minute. That certainly is okay to do, because this is nothing other than just a disguised form of 1 as long as x is non-zero. And I'm letting x go to infinity, so x is definitely non-zero. When you do that and distribute it through the top and the bottom, you rewrite the function in a new way. Like this. This is the exact same function right there as the original, as long as x is non-zero. But again, we're letting x go to infinity, so x is definitely non-zero. The benefit of this is now I can use the property that the limit of a quotient is the quotient of the limits, at least assuming the bottom limit is non-zero. I can write this. I could not do that with the original fraction. And the reason I could not do that with the original fraction is because both the top and the bottom individually go to infinity in the original fraction. This thing. The top and the bottom get big as x goes to infinity. They both go to infinity. And so if I tried this, I'd be dividing by infinity. I'd have infinity over infinity. We don't want to do that. So you've got to use some sort of trick like this with this kind of problem. But now I use the fact that the limit of a quotient is the quotient of the limits. I'm implicitly assuming I'm not dividing by 0 here. And that is the case. And so because of that, I'm being a little sloppy by implicitly assuming I'm not dividing by 0. And now I have the limit of a linear combination in both cases. That's the corresponding linear combination of the limits. I can write the top as the limit as x goes to infinity of 1 plus 2 times the limit as x goes to infinity of 1 over x. And on the bottom, I've got a linear combination as well. I can write that as the limit as x goes to infinity of 3 plus 4 times the limit as x goes to infinity of 1 over x. I use the linear combination factor. So it's not a real-life application, but it's an application to a pure math problem. both cases I have a sum. The sum gets carried along for the ride, so to speak. And in both cases, the 2 here and the 4 there can be factored in front of the limit sign. To finish, you just need to evaluate these limits. The limit of a constant function is the constant function. Its graph is horizontal. Its outputs always equal 1 in this case and 3 in this case. So definitely the limits of both of those are 1 and 3. What's the limit of 1 over x as x goes to infinity? Pretty clearly that's 0. You're getting 1 divided by bigger and bigger numbers. They're getting closer and closer to 0. This simplifies to 1/3. Okay? So you've got some completion problems where you have to use this kind of technique. And you should be able to do it for Friday's exam as well. We're using these properties of limits in this way to get an answer. It's kind of a pain, you know, to actually have to write all that. A little bit of a pain. It's worth doing a few times in your life flow, in Calculus 1, at least if you're taking Calculus 1, like you are. Okay, just to re-emphasize these properties. These properties also carry over to continuity. Well, linear combinations of continuous functions is continuous, both at a point and on a certain domain, a certain set S. Again, if a and b are constants and f of x and g of x are functions, if f and g are continuous, then so is this linear combination. At wherever these functions are both continuous. Same with the product. The product of continuous functions is continuous. If f and g are continuous, then f times g is continuous. With quotients, if f and g are continuous, then f of x divided by g of x is also continuous, at least wherever we're not dividing by 0. These facts here would be then most appropriate to prove that rational functions, for example, are continuous wherever they're defined. Okay, if you use these facts. Okay? These are so basic you might say it's hardly worth even stating, but it is definitely worth it. Okay, these are actually pretty powerful facts. Proving these things, especially proving the first bullet points, really involves using that epsilon delta definition of the limit. That's a more important application of that epsilon delta definition, is to prove those facts up here. It's tricky. I'm not going to do it. Okay? You won't have to do it. I just want to appreciate that these facts are true, and they really are useful. We're finally to the derivative of a function at a point. Again, we did talk about derivative sum already, back in lecture 5 or so. Let's re-emphasize what we learned back then. Given a function f defined at x equals a, the book transitioned to using x equals a here instead of c. It doesn't matter, I can use a c as well. The letter doesn't matter. Okay? In the continuity case, c is a number. Here, a is a number. The derivative of f at x equals a, denoted by f prime of a, that little apostrophe symbol is a prime. Read that as f prime of a, is defined by the following limit if the limit exists. We've seen this before. We used it with the x squared function. It's the limit as delta x goes to 0 of the change in y, that's the numerator of the fraction, divided by the change in x. Delta y over delta x. A is right here. It's the the graph of y equals f of x. And delta x is, say, about that big. So that this number is a plus delta x. Then without the limit sign, the fraction represents the slope of a secant line. Remember that terminology? Secant line, a straight line connecting the 2 points along the curve. We draw this a little bit more extreme. The slope of that, delta y over delta x, f of a plus delta x minus f of a is the change in y. That's this vertical distance right there. It's change in y divided by the change in x. That's the horizontal distance right there. Rise of the limit. By putting the limit sign in here and letting delta x go to 0, we're letting a plus delta x approach a, and so these secant lines become more and more like the so-called tangent line, which looks about like this. Where tangent means kissing, essentially. The tangent line just kisses the graph at one point. More importantly, more precisely, it's the best linear approximation to the graph in the way. Right there is a comma f. What straight line does the graph look more and more like as you get closer and closer to a? Our textbook, and most textbooks in fact, don't write the derivative definition this way. Instead of using a delta x, they use an h. And I think I will follow that convention here, at least in chapter 2. It's a little less messy that way, you might say. Okay? But keep in mind that h is delta x. H is the change in x. We can describe this in a couple different ways, other than just saying it's the derivative. We can describe it as something called the instantaneous rate of change of f at x equals a. Somehow it's measuring how fast f is changing, is the intuition behind that. If f is representing your distance traveled, then the derivative at a moment in time is your speed at that moment in time. If you got a speedometer with something like this showing you your speed, take a picture of it at a certain moment in time. That's your speed. That's your derivative at that moment in time. This comes back to lecture 1 where we had these paradoxes. Can we really let h go to 0 here? Can we really talk about a speed when no time has elapsed? Turns out you can. Distance does equal rate rate does equal distance divided by time. And that holds true even as the amount of time that elapses goes to 0. It also turns out to define the slope of the tangent line to the graph at the point A from pathway. And this is really a definition, if you want to be technical about it. It's not something to prove. We're saying the tangent line is the line that goes through this point on the graph with slope equal to this limit, if this limit exists. So we know a point, we know the slope, we can find its equation. Do an example. Let f of x equal x cubed. You'll have some completion problems similar to this as well. And you should be able to do this for the exam on Friday. Let f of x equal x cubed, find f prime of 1, and simultaneously verify it exists. So we'll do the calculation to find f prime of 1, we will find it, it'll be a number, and therefore we can also say, hey, it exists. I found it. Okay, so here's the calculation. When we did that x squared example from 4 or 5 lectures ago, we did basically the same kind of calculation with the square function. Here we're doing it with x cubed. It's a little bit more complicated here. because it's x cubed. Remember, this goes back to the first few days of class. When you plug some expression into a function, here, look where I'm pointing here. You plug 1 plus h into this function, you've got to replace the x with that entire expression. So I need to take 1 plus h quantity cubed. Right, like that. F of 1 is 1. 1 cubed is 1. Don't forget to subtract your 1. How do you find 1 plus h quantity cubed? Well, you could take the time to actually work it all out by hand. Here are the details. 1 plus h quantity cubed is 1 plus h times 1 plus h quantity squared. 1 plus h quantity squared, you've got to use FOIL. 1 plus h times itself. First times first would be 1 times 1 is 1. Effectively, it's like I'm doing this product here. Outside times outside is h times 1 is h. Inside times inside is h times 1 is h. So I get plus 2h. And then last times last is h squared. Now to do this multiplication, start with the 1 over here and multiply it times every term. 1 times 1 is 1, 1 times 2h is 2h, 1 times h squared is h squared. Then go to the h and multiply it times every term. H times 1 is h, put it under the other h term. H times 2h is 2h squared. And h times h squared is h cubed. Now simplify by combining like terms. 1 plus 3h plus 3h squared plus h cubed. Some people can jump from here to here without any work because they know something. What am I referring to? How can you jump from here to here if you know some facts that I haven't mentioned yet? It's called the binomial expansion. It's related to something called Pascal's triangle, which starts like this. It goes on forever. You make some ones along the diagonals, and then inside here, you add up the two numbers just above the given spot to figure out what goes there. So 2 goes here because it's 1 plus 1. 3 goes here because it's 1 plus 2. 3 goes here because it's 2 plus 1. 4 goes here because it's 1 plus 3. 6 goes here because it's 3 plus 3. 4 goes here because it's 3 plus 1. The next row would be 1, 5, 10, 10, 5, 1. And these numbers, in particular this set of numbers, 1, 3, 3, 1, are the coefficients when you expand a binomial. Binomial means two terms. I'm expanding a power of. So if you knew that already, you could just figure that out from Pascal's triangle. Or maybe it's something you even memorized. If that's not something that you learned before, then you're going to need to do this expression, do this product. That's what I got here on the screen next. I expanded. Don't forget about the minus 1. If you forget that minus 1, then you make a mistake and you get the wrong answer. Sometimes people seem to forget the subtraction. Keep it there. It's got to be there. Because now the 1's cancel. You've got a 1 here and a minus 1. Those cancel to give you 0. And with what's left over in the top, each term has a factor of h. That can be factored out. Like that. So I canceled the 1's. And then I factored an h out of the 3 terms that were left in the numerator, here, here, and here. So I reduced all their powers by 1. And now you're at the point where you can divide out the h's because, this is really key, because as a function of h, that's a rational function of h that technically is undefined at h equals 0. Its graph has a hole in it at h equals 0. But it doesn't matter because what it equals when h is non-zero fills in the hole. And we can evaluate this by plugging in h equals 0. This is continuous at h equals 0. This hear me again, this rational function of h, right there, this is what I was emphasizing most of last week, equals this thing as long as h is non-zero. But remember, the value of the limit, if it exists, is independent of what happens at c. c is 0 in this case. H is the variable, so to speak. The graph of this rational function of h is exactly the same as this function of h, except at h equals 0. That function is a quadratic. I can tell just by looking at it that its graph is a parabola, probably doing something like this. But the original function has a hole, a point missing, at h equals 0. This is the graph of the original function. There's a point missing, but by dividing out the h's and getting this function fills in the hole. Its graph is that same parabola, but with the hole filled in. Its limit can be found just by substituting h equals 0 because it's continuous at h equals 0. That's why the holes in graphs enter calculus in a fundamental way. This is why, right here. Okay, this thing has a graph that looks like this, with a point missing, but it doesn't matter, the limit still exists, and equals 3. So that means the derivative of x cubed at 1 equals 3. Right back. Okay? If I asked you to find f prime of 2, you should be able to do that. If I asked you to find f prime of negative 3, you should be able to do that. The calculations are very simple, similar. In the time we have remaining, let's think about what this means geometrically. The derivative is slope and rate of change. And let's think physically as well. Let's pretend the same function, except now I'm using t as the independent variable for time. F of t equals t cubed is the position at time t. You could also think of it as distance traveled, say if t is greater than or equal to 0. Then f prime of 1 is both the slope of the tangent line to the graph at 1, 1, and the rate of change of the function at t equals 1. Okay? You're looking at this animation and listen to what I say here. So this blue graph is f of t equals t cubed. I want to interpret the meaning of its derivative at t equals 1. The brown line is the tangent line at t equals 1. I just found that the derivative is 3. That is the slope of that tangent line. You try to estimate the slope of this, you get 3. Take rise over run. For example, on the interval that I picked here, the rise is 3. It goes from about negative 0.6 or so up to positive 2.4. Negative 0.6 or so up to positive 2.4 or so. A rise of 3. The run is 1. I'm going from t equals 0.5 to t equals 1.5. 3 divided by 1 is 3. That is the slope of that brown line. The green line with the red point are other tangent lines for other values of t. I could find the derivative at other values of t. The slope that I would get would be the slope of the green line for any of those individual values of t. But get this, here's the key thing. Watch the red dots. This red dot on the horizontal axis is traveling at a constant speed along that horizontal axis. Watch it. It looks like it's going at a constant speed. The red dot along the vertical axis, however, is speeding up. It's not a constant speed. That's because the rate of change of the function gets larger and larger as t increases. The speed of this red dot keeps increasing. The rate of change is the same as speed. And it's literally happening in this picture. And at t equals 1, this red dot is traveling at 1 unit of distance, 3 units of distance per unit of time. Now I was not able to get the A to show the time here because of the way I did this, because I tried it a different way showing the time and it was just too herky-jerky. This is smoother. But let's just imagine counting time here. You know, you've learned to count time by like 1001, 1002, 1003, etc. Let's see if that matches how fast this red dot is moving. Ready? 1001, 1002. Okay, this is moving a little slower than 1 unit a second. 1001, 1002. Count about that fast. That's how fast this red dot is moving. Try it again. 1001, 1002. I'm trying to say 1 when it passes through the 1 and 2 when it passes through the 2. When I say 1001, at that moment in time, when I say the word 1, try to keep track of how fast this red dot is moving. It's hard, okay? Let me try anyway. Ready? 1001, 1000. Okay. It's moving, and it moves faster and faster. What I claim is if it, at this point, it started moving at a constant speed, it would reach 4 when I reached 2. That's obviously difficult to tell. 1001, 1002. It's higher than 4 when I reach k equals 2. But that's because it's speeding up faster and faster. Its speed is matching the slope. The green line's slope gets bigger, this moves faster. The slope of the green line is the derivative. The derivative is the speed at any moment in time. That's a mouthful as usual. It takes time to think about. We will think about this continually during chapter 2. We'll think about it some on Wednesday. Then after the test starting next week, we're going to think a lot about this a lot. You will get it, okay? If you put enough time in.
So is the, I might just be misunderstanding number 2, but is the derivative only the rate of change at t equals 1?
The f prime of 1 equaling 3 is the derivative at that value of t, but I could find the derivative at other values of t as well. And I could find other slopes. The green line is changing, illustrating that the derivative keeps getting bigger and bigger. It's speeding up. Okay, have a good day.